So another example, the International Space Station has an approximate mass of 400,000 kilograms. It's approximately 250 kilometers above the surface of the Earth and travels at 5 miles per second. What is the approximate total energy of the International Space Station as it orbits Earth? Okay, so energy of orbit will be the kinetic energy it has plus the potential energy it has. Now, it is constant, but since this is asking just for the approximate energy, then we can just use this portion here. We can find out how much kinetic energy it has, how much potential energy it has. Now, as a reminder in this equation, m, the lowercase m that I'm writing, is the mass of the space station, the object that is orbiting. So the mass that's in every term is the mass of the object that we're talking about the energy of. Capital M in my gravitational potential energy term is going to be the mass of the Earth, because that's what the space station is orbiting. So off the test notes in the astronomical data info, the mass of the Earth, 5.98 times 10 to the 24 kilograms. R in this equation is the radius of the orbit. So if we have the Earth here, space station here, we need R to be the distance from the center of the Earth to the space station. The problem has given us H, this 250 kilometers. So we need to add the radius of the Earth to that to have our total R value. So the radius of the Earth, 6.37 times 10 to the 6th. So R for the potential energy term is those two added together. Capital G is our constant. V. So they've told us it's traveling at 5 miles per second. But everything else is in SI units, so we want this to be in meters. In the test notes, if we look at the conversion factors, one of the conversions tells us that 1 mile is 1.609 kilometers. So 1 mile, 1.609, but I'm going to put times 10 to the third because I want the meters. So 8,045 meters per second. Okay, we're just looking for how much the approximate energy of the space station is. So we're not using conservation of energy because we're not relating two different moments in time. We're not relating an initial and final. We're just saying, okay, hey, this energy is kinetic plus potential. So the kinetic is the 1/2 mv squared. And then the potential, the negative g mm over r. Guess we really only have one sig fig. But energy. Now, having a negative energy does seem a little weird. Just as a reminder, negative energy is just this overall attraction. There is an attractive force between the space station and the Earth. And that's ultimately why we end up with a negative energy. So this one's different. We don't use conservation of energy because we're not relating to different locations, 2 moments in time. We're just looking at the orbital energy overall.